Okay, day 4. Today we're going to get into a parallel resonance circuit. Okay, yesterday we went through a series resonance circuit. Today is parallel resonance circuit. Okay, basically resonance, the same thing, is just in a parallel situation is quite different than when you have it in series. So we're going to go through the PowerPoint presentation, and if you want to get back to it or do it step by step, then you're free to do that. We'll put both this YouTube and the PowerPoint presentation on the assignments. So let's open up the presentation, and there it is. Let's get back to home. All right, let's go over to slideshow, the beginning. All right, again, so we're continuing on chapter 25, but we're looking specifically at parallel circuits today. So first, before we do that, we're going to do a little component review. Look at review of how the particular passive components that we want to use are charged and discharged, whether it be a capacitor or an inductor. We will again revisit the series connection results. Okay, what did we get there? And then we'll look at the parallel circuit. We'll use the another Excel mathematical simulation, and then we'll at the end discuss the most important feature of resonance, actually the tank circuit. It's commonly called a tank circuit, and we'll describe that. Okay, so what to begin with, we want to do the electric component review. Okay, and whoops. So electric components are categorized either as active devices or passive devices. And the difference between the two is basically that the active devices require a voltage or a power to be, a separate power to be added to those devices. And basically, those are your solid state devices, which we will get to eventually when we get to that semiconductor components. So, but the passive devices do not require additional voltage or power. They just use the existing circuit voltage and current. So the components that we're really interested in that are passive devices are capacitors and inductors. And these two devices, they're reactive devices, and they impede the current, which is unlike the resistor, where the resistor just dissipates the current in the form of heat, while a capacitor stores energy in electric field, and the inductor stores energy in a magnetic field. So capacitors and inductors are storage units. To begin with, capacitors, as you can see, it can be many different types. That's a variable capacitor. This is a polarized capacitor and a fixed capacitor. And normally we use just a fixed capacitor. Variable capacitors are actually used in radios, or they used to be used in radios to tune in a particular radio signal. Polarized capacitors are used actually in a lot of power supply circuits to maintain a steady voltage. Fixed capacitors are used for various reasons. And it's the fixed capacitors that we're going to be talking about mostly. So it's basically a two-terminal device which stores energy electrostatically in an electric field. It does not dissipate the energy. Instead, it stores the energy in the form of the electric field. And if we look at going back to what does it look like in charging and discharging of a RC circuit. In other words, we have a resistor and a capacitor in series, and we're going to charge it up using a DC current. As you can see, we've got a DC voltage. We flip the switch, and initially what happens that there's going to be a surge of current going through initially. The amount will be Vs over R, and that current that starts out is going to start charging up that capacitor until that capacitor gets its fully charged equal to the same voltage Vs. So we can see this graphically here. We start with a high current. Okay, the current starts the process, so the current always leads the voltage. Current and diminishes as the voltage increases to a maximum. The maximum is reached at 5 times the time constant being the product of the resistance and the capacitance. So in an AC circuit, though, we're not using a resistor here. We're just going to get an oscillating current going back and forth, an AC current. Okay, and basically, like I said, current leads the voltage. The current starts at a high amount, where the voltage starts at a 0 voltage. So the current starts by and charges up the voltage to a maximum. At the 90-degree interval, you get a maximum, and then it starts dropping off as you start to discharge it. Okay, and then you repeat the cycle after 180 degrees. So at 360 actually. Okay, so and what's the capacitive reactance is the capacitor's resistive value. In other words, what it's actually, how does it impede the current or whatever. It does it through the reactance XC, which is 1 over 2 pi FC. 2 pi F is an angular frequency, which is given by omega sometimes, so we can use either expression. But normally, in this class, we'll use this expression here. Okay, as opposed to the capacitor, the inductor is quite the opposite. It's also a two-terminal device. It's also called a coil or choke, a reactor. Two-terminal, stores energy, though, in a magnetic field, not an electric field. So it basically consists of an insulated wire coil around a core. And these are pictures of the way you can get various different inductors. Okay, they take up space, so we don't like to use too many of these actually, but we actually need to, and by filtering circuits. So how do we energize using an RL circuit, meaning resistance inductance? Basically, in this case, changing voltage does the trick. So we need a changing voltage which energizes the inductor, or creates an induction in the coil, and the current increases to an inductive steady state. So initially we get a voltage, and from that voltage we get a corresponding a current. As the voltage builds up to a steady amount, the current will drop to well, this is the voltage across the inductor will diminish as in an exponential manner. And if you look at it AC wise, then the inductance now is a linear, inductive reactance is a linear function of the frequency and the inductance. But as we said before, the current lags by minus 90 degrees. So the current follows the voltage and is 90 degrees away from it, as seen from this diagram right here, and shown also as a phasor down here. So IL is minus 90 degrees as compared to VL. And again, the governing inductive reactance, XL is equal to 2 pi times the frequency times the inductance. So as frequency goes up, so does the inductive reactance. And as the inductor value goes up, so does its reactance. Those are the equations that we are going to be using to figure out how what happens in a parallel circuit. So we have an electrical AC circuit containing a resistor, a conductor, and a capacitor, and they still exhibit resonance at that specific AC frequency when XC is equal to XL. That stays the same. So you get basically a resonant frequency equal to 1 over 2 pi times the square root of LC. So it doesn't matter if it's series or in parallel, we're going to have the same thing. Resonance in the case of a series circuit, though, we get a current peak at that resonant frequency. And so we can use, in a series circuit, we can use that to select and create a specific signal frequency output from the circuit, which we will essentially filter around. And we also found out the optimum output is when we take it across one of the reactive components. So here is the figure, the circuit using the same components as we used for the series circuit, only we added a little 10 ohm resistance in series with the inductor, because that's normally what the case. You never get an inductor that's just purely inductive. It always has a resistive element to it in series with the inductor. Okay, so that's what the circuit looks like, and we're energizing it with 300 microvolts and the resonant frequency we said is at about 1,000 kilohertz. So we're imposing that, and we're going to get resonance in that rectangular circuit there, which we call a tank circuit. It's called a tank circuit because basically what we're really doing is we're charging it up with energy. So we're gonna fill this tank circuit up with energy. And that energy is just gonna flow back and forth, okay? So first the capacitor is gonna charge up the inductor, and then when the inductor is fully charged, it's gonna go back and charge up the capacitor. It keeps going back and forth, like so. So the reactor currents should be equal in magnitude at 180 degrees out of phase from each other, because if this is a capacitor is leading current and the inductor is lagging current. So that's what happens. So they basically are 180 degrees from each other. So let's create our spreadsheet again like we did before. We'll look at the frequency range as we did from as shown here. We'll evaluate the inductive reactance and the capacitive reactance depending on the frequency and what the resistor value is. Okay, resistor values. Okay, and from that we will also figure out what the current is across the capacitor and the current across the inductor. Okay, we get, and basically we'll look at the value of the difference between IL and IC. Okay, and obviously it'll be different depending on where we are relative to the resonant frequency at 1,000 kilohertz. Okay, 1,000 kilohertz, we switch where IL is greater than IC to IC being greater than IL. Okay, and so we get a total current going through there, and we notice that at 1,000 we get a very small number. Okay, we get a very small number. But and impedance-wise, we could figure the impedance, which is a function of XL and XC. We're ignoring the low 10 ohms. It really doesn't add much to it. Okay, so that's our impedance. And our impedance at 1,000 is maximizing, or our line current is minimum. All right. Okay, so let's see if that shows up. Well, here's our graph of the impedance, and as we said, at 1,000 we peak in impedance. So in a tank circuit, basically what happens at the resonant frequency, we get a peak in impedance. Okay, it means very low current. And there we show it. At impedance, at the resonant frequency, that current drops to just about zero. Okay, and that's what that shows. So that's totally opposite the effect of when we have it in series. However, if you want to look at the currents running through the inductor and the resistor, and the inductor and the capacitor, again, we see the same as we saw in the series event, that they are opposite one another. Okay, they are opposite. Cap current versus inductive current, they're opposite, and they're 180 degrees apart from each other. Because one component is charging while the other is discharging, and vice versa. So what are the differences in the series versus parallel? Series versus parallel circuits. Series, the current is the maximum at resonant frequency, where in the parallel resonance, the line current is minimized at the resonant frequency. And the current in the series is in phase with the generator, because there is a net zero reactance. So it acts like it wasn't even there. There was no resistance there. Okay. In the case of the parallel, IT current is in phase with the generator voltage, though. Okay. So in series, the voltage across either the inductor or the cap is max. So that's where we take the output from. Okay. Whereas here in the parallel circuit, the impedance, which is the applied voltage over the current, is maximum at FR because of the low IT. Okay, so you can see if this is very low, then the impedance VA over IT is going to be, if this is high, VA over IT is going to be very low. The individual currents in the resonant parallel circuits may be significant, though, because even at such a low current, that allows us to use it as a filtering device, get an output from it. So here's a picture. Now we can basically show that in the case of a series cap and inductance series, if your frequency below the resonant frequency, you're basically acting capacitively. If you're above that resonant frequency, you're behaving as a inductum. And the opposite is true for parallel capacitive inductive sensitivity. Okay, at lower frequency, you're inductive, and at higher frequencies, you become more capacitive. Okay, so that's it. And tomorrow we will end with some things about resonance.